Hi, my name is Miss Plant and this is a first in a series of videos in which I'm going to go through the AQA A Level Physics specification in as much detail as possible, so that although this can't prepare you for all the possible questions they could ask on the exam, at least it is the best preparation you can get. So first bit is measurements and their errors. They all have codes, so like it starts with 1 introduction, then 2 is the spec at a glance, and then the codes begin with 3. So 3 is really just the content, and then 1.1 is the first bit here. And the first bit 1 is measurement and their errors, and the first bit of measurement and their errors is the use of SI units and the prefixes. So that's what I'm going to go through now. So there are 7 SI units, however only 6 of them are examinable. The 7th one is the candela, which is the fundamental unit of light intensity. So these SI units, System International Units, are often known as the fundamental units, as in they can't be broken down into anything else. They are the end point for the units and measurements. So for example, time, T is measured in seconds, or S. Length, often given L or X or S, sometimes for displacement, is given in meters. Mass in kilograms. Current, which is I because it's intensity of current, in amps. Temperature, T, I guess sometimes theta will be for degrees Celsius, in Kelvin. So temperature is measured in Kelvin, which is something you cover in the year 13 course, or if you do A-level chemistry as well. And then amount of substance from chemistry, GCSE or A-level chemistry is N, and that is the mole. So these are the 6 base units by which we measure things in the world. They are the base units. We can use them to derive other units. So for example, you might have noticed a unit like the newtons. A lot of the derived units are named after white gentlemen. So force, the unit of force is the newton. Now that's a derived unit, and we can find out the base units which can be used to kind of make up that unit. So we just have to use a bit of forensic work. I quite enjoy this. We think of an equation that can be used to make the Newton in terms of other units, in terms of these 6 SI units. So the first one that comes to mind with force is equal to mass times acceleration. Unit of force is the Newton, unit of mass is the kilograms, unit of acceleration is meters per second squared. So therefore the Newton is the same as kilogram meters per second squared. So Newton is a derived unit. This is the Newton in terms of the base units, right? I'll give you another example. So energy is joule. Now energy, work done is force times distance, right? So work done, which doesn't have a handy letter, is force times distance. Sometimes you see it as force times S, where S represents displacement. So the work done, which is the energy, is the force times distance. So well, that's the newtons times the meters. Will be the joule. And we know from here where we've worked out what the Newton is. So the joule is the kilogram meters per second squared times meters. And then if I just make that a bit tidier and collect the like terms, I see that in terms of SI units, or in terms of fundamental base units, the joule is kilogram meters squared seconds to the minus 2. There's other ones you can do. There's power, there's volt, there's the charge, coulombs. There's lots of other ones you can look at and try and investigate. Basically, think of any unit. You can always break it down and write it in terms of these 6 fundamental things that we measure, or the 6 base units. Now, quite often these base units in themselves are pretty minimalistic. So length, quite difficult to measure things in meters if we're talking about the scale of the universe or the size of the atom. So we add prefixes before them, before the SI units, in order to be able to change their order of magnitude, to be able to change multiply it by a factor of 10. All these things should be written in standard form. Standard form is when you write a number as any number, so say 3, then times 10 to the power of, and then another whole number, so minus 3. So that's 0.003 written in standard form. This needs to be a number between 0 and 10, and this needs to be just a whole number. That's written in standard form. You need to be able to give numbers in standard form. So these prefixes, though, kind of like shortcut the standard form. Some of them are quite familiar. So, for example, centimetres, that's 100th of a metre. So that's times 10 to the minus 2. Millimetres, it's 1,000th of a metre, times 10 to the minus 3. They apply to all of them, but I just find metres the handiest one to kind of figure things out. Kilometres, that's 1,000 meters. So that's going to be times 10 to the 3. Then once I've got those in place, they just kind of work their way up. So megameters is times 10 to the 6, gigameters would be times 10 to the 9, and terameters would be times 10 to the 12. And then getting smaller, we got times 10 to the minus 6 for micro, times 10 to the minus 9 for nano, times 10 to the minus 12 for pico, and times 10 to the minus 15 for femto. So sort of from like, and this is the joy of physics, and one of the great things about the subject is we're kind of thinking about femtometers when we talk about what goes on in atoms, all the way up to terameters and beyond, really, when we're thinking about the universe and how far away other things are in the universe, which is very far. There are others, actually. They added some. If you have a look at it, you can work out the new prefixes and do a bit of research about that, but that's not required. Now, the other thing you need to be able to do is you need to be able to convert between different units of the same quantity. So joules, electron volts, and kilowatt hours are all units of energy. In short, if you're thinking about very small amounts of energy, you'll use an electron volt. If you're thinking about a very big amounts of energy, you use the kilowatt hour. So when you have an electricity bill, you get your how much electricity you've used, how much energy you've used through the transfer of electricity in kilowatt hours. So just to make it a more manageable number. So 1 electron volt is the energy one electron gets when it's accelerated through a potential difference of 1 volt. It's the same as the charge on an electron. So 1 electron volt is the same as 1.6 times 10 to the minus 19 joules. So to convert, if you go one way, you're going to be dividing by 1.6 to go from joules to electron volts. If you go the other way, you're going to be multiplying by 1.6 times 10 to the minus 19 to go from electron volts to joules. Kilowatt hour is slightly trickier. So the kilowatt hour is the energy used by a 1 kilowatt device if it's powered on for an hour. So the easiest way potentially is thinking about the watt hour and what that would represent. So 1 watt is 1 joule per second. And if you use a watt for an hour, it's going to be 1 joule per second for 60 seconds, and then for 60 minutes. So it's 60 times 60. So it's 3,600. And then if we add in the kilo, we multiply that whole thing by 1,000. And we get 3,600,000. So this is from the seconds and hours, and that's from the kilo, is equal to 1 kilowatt hour. Normally, we wouldn't write it like that. Nobody wants to be counting those zeros. So we write 3.6 times 10 to the 6 joules is equal to 1 kilowatt hour. So going that way, you're going to divide from joules into kilowatt hours, divide by 3.6 times 10 to the 6, and going the other way, kilowatt hours into joules, you're going to multiply by 3.6 times 10 to the 6. That's the end of the first section.